Hey guys, today we are going to be modeling exponential growth and decay by performing transformations. So we are going to possibly take a look at a data set where a linear model may not be appropriate. So looking at how we can apply transformations possibly with logarithms. Okay, so I know it might be a little bit since some of you have seen logarithms, but we'll try and explain that within here today. But by using logarithms to help find a model that better fits the data. So if we were in class right now, you would have been given a bag of M&Ms, you and your partner, with 60 M&Ms in it. So it says, shake up your bag of M&Ms, pour them out in front of you, and count the number of the total number of M&Ms. So I prepared my bag, so I had 60 M&Ms. It says record this amount to the right of trial 0. So I put 60 M&Ms in my bag, so I'm going to record that for trial 0. Now it says shake it up, and I am going to pour out the M&Ms. Okay, and notice that M&Ms either land with M's face up or M's face down. So it says remove the amount of M's up because they have decayed. So now I could eat these. So this would normally be pretty fun to do in class. Record the total number of M&Ms remaining next to trial 1. So after they've decayed, so I'd remove the ones with M's. Okay, and these would be my ones that have decayed. And I would record how many were remaining in my table. So to save a little bit of time, I am just going to give you that I had 30 remaining, okay, because I did this already. And then I shook my bag up again, poured them all out, and now I only had 16 remaining because the rest had M's faced up, so I ate them all. And then I had 7, 4, 3, 3, 2, and 1. Okay? So it says, record the number of M&Ms remaining next to trial 2. Continue this process for at least 5 trials or until all M&Ms had been consumed. Okay, so I still had one left that didn't have an M face up, so that's why I still had 1 remaining. Step 2, enter the number of trials of in list 1 and the corresponding data in list 2. Plot the amount of M&Ms remaining Y against the trial X and describe the pattern. So I need you to take out your calculator, and then we're going to go to a list. So I'm going to go to Stat and then Enter for Edit. I am going to arrow to the top so the list number is highlighted. Hit Clear and arrow down. I'm going to clear out the data in my list 1 and list 2. Okay, so now go ahead and put the trial numbers in list 1. So we had 0 through 8. And then the number of M&Ms remaining in list 2. So we're going to make a scatter plot of this data, okay? So in order to make a scatter plot in our calculator, we go to second, y equals, turn our plot on, our first plot on, select scatter plot, which is the first data display. I want it to mark list 1 and list 2, and using the little boxes are just fine. So I'm going to go zoom 9. Okay, and that's what my data looks like. So I did a scatter plot of list 1 and list 2, and that's what my data looks like. So it says, describe the pattern. Well, notice as my number of trials increases, the number of M&Ms starts off by decreasing rapidly and then kind of begins to level off. So, sorry, so my M&Ms in the way. I didn't get a chance to eat them all. As the number of trials increases, the number of M&Ms starts off by decreasing pretty rapidly. Then begins to level off. Okay, you're just simply describing what you noticed. We also noticed there tended to be a negative association because as the number of trials increased, the number of M&Ms remaining decreased. So we can mention that. And some of you might have noticed that this looks like exponential decay, possibly. Okay? So the next one says, check to see if y is being multiplied by about 0.5 each year by calculating the common ratio. Okay? So right here, in order to figure out the common ratio, okay, I do 30 divided by 60. And yeah, that was being multiplied by 0.5. Okay? But then when I do 16 divided by 30, that's a little bit different from 0.5. That gives me 0.53. I'm going to erase the multiplication. We'll say 0.53. And then 7 divided by 16 to get that common ratio. That was 0.4375. 4 divided by 7, about 0.571. 3 divided by 4, we know is 0.75. There wasn't change here. 3 divided by 3 is 1. 2 divided by 3 is 0.6 repeating, and 1 divided by 2, 0.5. So sometimes close to 0.5, sometimes exactly some 0.5, sometimes off. A common ratio greater than 1 is an indicator of exponential growth. So that clearly this is not exponential growth. If it's less than 1, it's an indicator of exponential decay. Great. That's what it looks like it was. Okay, now for the next one. It says, in list 3, take the logarithm of each number, y. So in list 3, we are going to enter this right here, log of list 2, in the top of list 3, and plot the logarithms against the trial number. Okay, so we're going to make a scatter plot of list 1, comma, list 3, and we're going to describe the pattern. So first, let's get information in list 3. Okay, so I'm going to go back to my list, stat and edit. And I'm going to arrow to the top of the list so the list number is highlighted. And I'm going to type in my formula. I'm going to type log, okay, which is right off to the left, 4th button up, so log. And then I got to type in list 2. All the list numbers are in blue above the numerical values. So list 2 is in blue above the number 2. So I'm going to hit second, number 2, close my parenthesis, and hit enter. Perfect. I got values right there. Okay, so now it says it wants us to make a scatter plot of the trial number and then the logarithm of list 2. So I can go back to my scatter plot, second y equals, and now instead of list 1 and list 2, it wants list 1 and list 3. Let's take a look at that. Remember, the window that gives us a good window for all these graphs is zoom 9. Whoops. There we go. Okay. So what do we notice here? Well, it looks like for strength, it looks like strong. For direction, it looks negative. Okay, so I'm going to say form, it looks linear. So here, there appears to be a strong negative linear relationship between trial number, because that was list 1, and now what was list 3 that we graphed? It's the log of the remaining M&Ms. Okay, so let's take a look at the back. The back says, for step 5, calculate the linear regression equation R and R squared using the data in list 1 and list 3. Describe the strength of the relationship and record your least squares regression equation below and in your calculator under Y1. Okay. So I'm going to find my least squares regression equation using list 1 and list 3. Okay? So I'm going to go back to my home screen and I'm going to go to Stat, go over to Calc, and number 8. And remember, my X list is going to be list 1, but my Y list here is going to be list 3. So hit second number 3, and then you can just enter on through. Okay, so there's our equation, and we've got R and R squared coming up, which is good. Okay, so I'm getting my equation, my A value. So the log of Y hat, because remember, we took the log of the original data points in list 2, equals, let's round to the nearest hundredth, 1.627 minus 0.208x. Okay, my R value is negative 0.976. And my R squared is 0.953. So based on this R value, what does it tell us? Well, it kind of confirms a little bit what we said in step 4, which was that there is a strong negative linear relationship between the number of trials and the log of the remaining M&Ms. Okay, and then what about R squared? Let's practice interpreting R squared. Okay, now remember, anytime we write a least squares regression line, we should be labeling what X and Y hat are. So just a little reminder up here, Y hat is the log of the predicted remaining M&Ms. And remember, X was your trial number. Okay, Just a little recap of how to interpret r squared. Let's interpret, what does this r squared value tell us, okay? R squared tells us that 95% of the variation now it's the variation of your response variable, or y, okay? So it's the variation, the log of the remaining M&Ms. Can be explained by the linear relationship between trial number and log of remaining M&Ms. Okay? Just to give us a little bit more practice interpreting r squared. So now it says, construct and interpret a residual plot for log of y hat on trial number. And your equation from step 5 is y1. Okay, oops, we need to put that into our equation for y1. 1 second, we're going to do that first. So go to y equals and enter that equation. 1.627 minus 0.208x. Okay. So it says, so we're going back to step 6, where it says, if your equation from step 5 is in y1, all you need to do is enter list 4 as residuals, and these values should appear under list 4. So let's go back to our list, go stat, and then edit. Now this time we're scooching over to list 4, highlight list 4, and then we need to find our list of residuals. So if we go to second stat for list, you'll find resid for residual, and there you go, it should give you the residuals. To check your residual plot, plot list 1 against list 4, okay? So we're going to make a scatter plot, which is also a residual plot here because we're plotting the residuals. So list 1 comma list 4. So when I go back to my scatter plot, I need to change it so it's list 1 and list 4. So second number 4 for the Y list. And again, zoom 9. Okay. Whoops. It's graphing I'm going to turn off that real quick. There we go. Okay, so go ahead and sketch a graph of your residuals. You could label the units. You could hit trace if you wanted to on your calculator, if you wanted to get specific on where your units were and whatnot. And then it moves it. If you use your arrows, it moves from key to key. I'm going to add some more increments in here. So I have 8 for my trials. You know, just a sketch. It doesn't need to be this close. It's up to you. Okay, so maybe something like that. Okay, so does it appear that the values are randomly scattered above or below the line? Okay, hopefully you recognize that there appears to be a curve pattern. There is a curve pattern in the residual plot. Therefore, the transformed, because we transformed, this isn't our original model, therefore the transformed linear model is not appropriate. Okay, so now it says we need to transform the linear regression step 5 back to the original units. This requires an inverse transformation. Since we took the logs of each y value in step 4, we simply undo this step by taking the equation in y1 as an exponent of 10. So in y2, we're going to enter, so go to y2. I'm going to hit 10 raised to the power of my equation from y1. Whoops, sorry. 1.627 minus 0.208x. Plot your new exponential equation in y2 against the data in list 1 and list 2. So now I'm going to plot this equation with my original scatter plot from list 1 and list 2. So I can go back and change my scatter plot to list 2. Wow, that's a pretty close fit. So this curve seems to be a much closer fit to almost all the data points. So the curve seems to be a much closer fit to almost all of the data points. Okay, so using your new exponential equation in y2, what is the predicted number of M&Ms for trial 3? Okay, so I'm going to use my new equation y2, which was y hat equals 10 to the, I'm going to go back to y2, 1.627 minus 0.208x, but it says I want to know for trial number 3. So I'm going to take 3 and plug it in for x. So 1.627 minus 0.208 times 3, and then it's going to be 10 to the power of that. So what is the predicted number of M&Ms? About 10 M&Ms, okay? According to our new model. Okay, and with our original, I mean, this could change with every sample, right? If I were to have you guys in class, this isn't going to necessarily be your data. This is different. It could be different. So we predicted about 10. We had about 7 in ours. So we're able to make a transformation to better fit our original data set in list 1 and list 2 that clearly was not linear. Okay? Good luck on your homework tonight, guys, and bring any questions that you have to class the next day.